am in the third year laboratory of Department of Physics. This is basically optics and modern physics laboratory. So, in this laboratory we have the setup for observing the Faraday effect. So, this is the experimental setup here. We have arranged this experiment. So, as I told this, there are two components, main components in this experiment. One is light, another is magnetic field. So, light, this is the light source, this is the light source. So, white light basically it has all sorts of wavelength, it is coming. Okay. Now, here we have used a filter, one filter I have put this looks color looks green, okay, looks color green. So, this light will this light, this filter will select a particular wavelength. So, that what is the wavelength it will select, that that is there written on this filter is a basically interference filter, very good, one need very good filter. In filter main problem is the absorption of light. Okay. So, if filter quality is good, then you can get absorption will be less. So, intense light you can get for a particular wavelength, as well as quality of filter decide the bandwidth of this of the wavelength. Okay. So, so now this from the filter light of a particular wavelength will come, and this is the polarizer. So, it will fall on this polarizer. So, light will be polarized light, okay, plain polarized light. So, that light will, so here will fall on the sample. This is the sample here, this is the sample, okay, between two pole pieces of the magnet, because we have to apply magnetic field. So, so for the magnetic field, what is the arrangement, that I will tell you, but before that let me finish that. Light will fall on the sample and pass through the sample, okay, and that light then it will fall on the another polarizer. We tell this the analyzer, basically polarizer and analyzer are same. So, so it will fall on this analyzer. Okay. So, if both initially, if both polarizer and analyzer we keep their axis, optics axis keep the parallel, and for that we will get intense light. So, here we have used one lens, and this is the screen. So, one can use also photodetector to see the intensity of light. Basically, we have to measure the intensity of light. So, here we have used one lens, and then this is the screen. On the screen you will see the spot of the light coming. So, now actually we have kept this this polarizer and analyzer in cross position. In parallel position we do not keep, because it is difficult to see the change of intensity from bright. It will be less bright. Okay. So, it will not be, this measurement will not be sensitive, but initially if it is dark, then from there it is becoming slightly bright, and to make it dark, how much we have to rotate the optics axis, means this analyzer, okay, from the cross position, how much we have to rotate. So, that much basically this, that will be the angle of polarization. Okay. So, so that we have to measure. for different magnetic field and for different wavelength. So, now you see these different wavelength, how we will select? We will use different filter. I have different filter, okay. I have different filter and wavelength is written, this is red color, means this wavelength will be I think here is 565, okay, 565 angstrom or 595, sorry, it is written this way, it is written this way, it is a 595, okay, 595 angstrom or 595 nanometer or 5950 angstrom, okay. So, this is red one. So, then I have other this, it is the blue one, it is the blue or violet one, okay. So, what is the wavelength, that also it is written here. So, anyway, so it is written. So, for different I can select 5 wavelengths. So, I have here I have 5 filter, I can choose 5 wavelength, okay. So, for each wavelength, then what we have to do, we will apply magnetic field. For 0 magnetic field, first we have to set for a particular wavelength and then we will change the, we will apply the magnetic field. How you are applying? So, you can say this is the electromagnet. So, this is the electromagnet and these two are called pole pieces, okay. So, magnetic field will produce between these pole pieces where we have kept the sample. Now, now we have to, if we pass current through this coil, so that that means we need the power supply for constant current. So, this is the power supply, this is the power supply, okay, for constant current power supply. So, here you can see is the, here we can change the voltage and here we can get the current. If we change the voltage, okay, so then current will vary. So, we will set at a particular current and for that current what is the magnetic field between these two pole pieces where we have kept the sample or we will keep the sample, that we have to note down. Now, as I mentioned that magnetic field along the axis of the pole pieces, it will vary. It generally it varies like this, it is like Gaussian forms, okay. So, at different position we have to put the probe, Hall probe, okay. So, that from Hall probe is basically part of the Gauss meter or Tesla meter. So, this Tesla meter or Gauss meter will give the reading of the magnetic field, okay. So, we will apply from the power supply, we apply a particular current. For that, what is the field between these two pole pieces, mean field between the two pole pieces, that we have to measure for that current, and to get the mean magnetic field. So, at different position on the sample, okay, in absence of the sample. So, at different position between the pole pieces we will measure the magnetic field, then we can plot it and then from that plot one can find out the mean magnetic field, okay. So, so that we have to do. So, for that we will use probe, as I told I will show you probe or and Gauss meter. So, this is the Gauss meter, it has a probe. So, it will give me reading initially, now it is reading is 0, okay, because I have not applied any current or it is away from that magnet, okay. So, now here this is basically is the Hall probe. I will in separate class I will when I will discuss basic tools and instrument in a laboratory, during that time I will discuss about the principle of this Hall probe. So, here basically this probe basically a transverse probe, okay. Here magnetic field, if I want to measure between two pole pieces, so I have to apply like this, okay, perpendicular to the axis of the pole piece, I have to apply this way. So that is why it is called transverse mode, okay, transverse probe. And but here we want to magnetic field along the axis, okay, and inside the, you see, sample also it is inside the pole, okay. So I cannot put here inside this, so I have to put this one like this along the axis, I have to measure the magnetic field, okay. So for that, this is the special type of pole pieces, there is a hole between inside these pole pieces. So through hole I have to put the probe, so this probe then it cannot measure, okay. Condition for this probe, the magnetic field has to fall on this perpendicularly, okay. So if I put this way, magnetic field will fall like this, like along the axis, okay, along the length, okay. So that is why we have to use special type of probe, it is called axial probe, okay. So it is this on the axial probe, I will not use that one. So that axial, so I have to, for measuring that one, this should be, I have to remove that one, okay, and then I have to put this probe through this hole, and for different position I have to note down the magnetic field. So instead of that, just I will just to demonstrate, I will show that this can be used for measuring the how magnetic field we are noting down for a particular current of the pole pieces, okay, current passing through the coils of the electromagnet, and magnetic field produced because of that between the pole pieces. So that I will tell you later on after disturbing this arrangement, because if I disturb now, then it will take time to align it. So let me demonstrate the experiment first. So what we have to do, the experiment, first experiment, as I if you see the data. So this is the basically, here we have put this type of rod, glass rod, okay, is transparent, it is transparent, okay. This is the length L, small l, in formula you have seen. So that is given, or one can measure, okay. It looks to me around 2 centimeters, 2 to 3 centimeter, okay, that one has to measure, or it will be supplied, okay. Now so already this same sample, okay, we have put there. So I am not going to disturb that one, that's why I showed you another piece. Now here we have used this, as I told, this one filter we have used there, this is the, I think it looks green color, okay. So some wavelength is there, it is written on this filter, so that one has to note down. Now what I will do, I know first before starting the experiment, as I told, either before starting the experiment or after the experiment, one can calibrate the magnetic field. One can calibrate the magnetic field means magnetic field versus current, mean magnetic field for different current, okay. So that one has to find out. So how to find out the mean magnetic field? For that, at different position along the pole piece, okay, we have to measure, from that we have to find out the mean magnetic field, okay. Now if I have not applied any magnetic field here, you can see this 0 reading of the power supply, okay. Now in this condition, here you can see, now it is in cross position. Here you can see that I have put here a scale is there, okay. Here top here it is 0, this side 90 degree, other side minus 90 degree. So, you can rotate it by 180 degree. Okay. So, now it is at 90 degree and it is at, you see, this 0 degree. Exactly it is not at 0 degree, but more or less it is in 0 degree, because it is because these two we have put here, it is not perfectly aligned. So, it may be slightly rotated during the aligning the things. So, if you do the perfectly alignment, then this also will be at 0, but not necessary. So, say I just disturb it, okay. I just disturb it. What you will see here, you can see green light, green spot you are seeing, okay. So, if I maximize this green intensity of the green spot, so I will rotate it, okay. I have to make it if both are aligned, so intensity, so it should be also near the 90 degree, okay. So, what is the value now? It is at 90 degree. It is at 90 degree. You see, this is at 90 degree, that is also at 90 degree. Okay. So, intensity here, spot you are seeing, this is bright spot, as I told, polarized light. Now, without changing the angle of polarization, it is falling on the analyzer. So, all light passing through it. Okay. So, now from this condition, I will go to the dark position. As I told, dark position will take the initial condition. Okay. So, now I am changing this one and I want to see that at which position I am getting the dark one. You see, becoming dark, this. I think this is the dark spot, more or less. So, one has to adjust here, yeah, more or less I have come to the same position as I or slightly more one can go, or I have gone more. So, one has to basically adjust. Okay. So, as I am showing you, one has to basically adjust. Yeah, I think this is the dark condition on the so that way one has to perfectly try to find out the darkness. There should not be any light pass through this, then they are in cross position. So, this is my initial position without magnetic field. Now, I am applying current. Okay. So, here I can apply maximum 0 to 4 current, 4 ampere current. So, let me go to the maximum current. Okay. So, we will see the maximum effect, okay, maximum magnetic field, but you have to do for 1 ampere, 2 ampere, 3 ampere, 4 ampere. Okay. So, that means for 4 different current, what is the magnetic field that you are finding out, because you want to do the experiment for this 4 current, okay, 4 magnetic field. Or if you want to take more data, then 0.5, you can take the step of 0.5 ampere. So, 0.5, 1, 1.5, etc. So, 8 set of data for different magnetic field, you can do the experiment. So, one has to decide. So, now let me apply. So, this is the darkest condition, okay, in cross position. Okay. So, whatever the polarized light is coming, so here it is falling at 90 degree. If that is that we tell this polarized light, it is the here we kept in this. So, light polarized that it is, if it is said in this direction. So, here optics axis this direction. So, it is in cross position. Okay. Now, if I apply magnetic field, so this polarized one, if it is just slightly rotate either this direction, the other direction, so there will be component along this direction. Okay. So, that component will pass and we will get the some intensity. So, let me apply the magnetic field and see the one has to see there. So, let me apply magnetic field, say here I am changing the voltage and corresponding current is I am setting at say setting at 4 ampere. So, fine one I can adjust. Okay. Exactly, it is 4 ampere. I am interested about the current, not about the voltage. So, for getting 4 ampere current, what is the voltage I need? Yes, I can, you can switch off this light then. So, I have applied 4 ampere, it is slightly changing, more or less is 4, now it is 3.97 ampere. So, here I think you can see this spot of light. Okay. So, if that light I think it just I think you can see. Okay. Now, what I have to do? Now, here I have to take reading. Okay. In this condition, what is the reading of this analyzer? Okay. So, here it has the scale, vernier scale also, that I will show you later on. Okay. So, one has to note down this reading, and now I will rotate that one, okay, to make it dark. So, how much I have to rotate that? I will, one has to rotate it, but it becoming more dark. So, slightly I have to slightly, very slowly I have to rotate and make it perfectly dark. Okay, it is more or less dark. Okay, slightly more I can rotate, but okay, but still let me check it. No, becoming dark. Yeah. So, one has to do carefully. Okay. More or less its intensity decreased. So, one has to tune properly, but since I am trying to show you in the video, it is yeah, it is you can use the light. So, in same condition they can see. Now, you cannot see. Okay, you cannot see this because in dark condition I have. So, these more or less one has to very precisely one has to rotate and find out the dark condition. It may not be perfectly dark, but one has to find out. So, now I have to take reading of this one. Here for taking reading, you can see here this is the one scale, main scale. Okay. And here if the scale is there, another scale is there, that is the basically vernier. Okay. So, here 10 divisions are there, and we have seen that these 10 division coincide with the 9 division of the main scale. So, each division then vernier constant is basically 0.01, okay, 0.01 degree, because these the in degree. Okay. So, 1 by 10, 1 each is 1 degree. So, 1 by 10. So, 0.1 degree, sorry, not 0.01. So, 0.1 degree is the vernier constant. Okay. So, that means here from here directly you can find out the rotation, angle of rotation from initial reading and this now second position reading, and reading you will get like 10.1 or 2 or 0.3, 0.5 etc. So, accuracy here you will get 0.1 degree. Okay. So, for these two position you note down the reading and find out the difference of that will give you del phi. Okay. So, that will give you basically whatever we are telling the del phi. So, that you will get that you have to note down. So, I have to reduce the current, because the highest current I have given. If you keep it for more time, then it will be hot. Okay. Then magnetic field, accurate magnetic field you will not get, it will fluctuate basically because of the temperature. So, I will reduce this one. Okay. So, so I have to just reduce the, I have reduced the voltage. So, current is more or less 0. Okay. So, let me show you the, so this is the for magnetic measurement, that I will come later. So, angle, so just I showed you the angle of rotation of the polarization plane as a function of magnetic field. Okay. As a function of magnetic field for different wavelength. So, we have chosen a particular wavelength, so that we have to note down here, it is written on that filter. Okay. Now, magnetic field. So, here this, what is the current you are applying. So, 4 ampere I applied. So, for that, what is the mean magnetic field, that from calibration we know. So, that magnetic field and corresponding rotation here you have to note down. Okay. Yes. So, for a particular wavelength. Now, for second wavelength, for different magnetic field. So, only one magnetic field I have showed you, for one lambda I showed you. So, for second wavelength, for different magnetic field, okay, you have to do that, but that is the mean magnetic field. So, mean magnetic field, how to find out, I have described. So, this way you will find out the angle of rotation. Okay. So, now from here you know the what is the wavelength, and for that what is the Bhadet constant, because for that wavelength this from this magnetic field and this del phi, okay, from that either plotting graph you can find out the slope from del phi by b. Okay. In that formula you have seen this Bhadet constant is del phi by b l. Okay. So, del phi by b, from this del phi by b. Okay. So, this one, now only I have to see this actually I forgot this 2 rotation 2 del phi. Why we are taking, not taking del phi, we are taking 2 del phi, that I forgot to what is the reason, that let me 2 del phi, we are taking double rotation. But in formula it is not coming double rotation, it is del phi, angle of rotation of plane of polarization, nu is called Bhadet constant. But what is the reason exactly I forgot, but I can tell you. B I will find out from their mean magnetic field for different coil current. So, I think nothing to do with the 2 del phi. In experimental formula, I think as a function of magnetic field measure del phi rotation of polarization for each selected wavelength, plot it and find nu, then plot nu versus lambda curve. I do not know, but I do not see any reason for written 2 here. Actually, in my opinion, it should be del phi. It should be del phi, but why I have written 2 del phi? particular reason I cannot tell you right now, but anyway, but it's whether it is it's a rotation, say light is coming and then it's not reflection, so or something we are not rotating. Anyway, so I think it should be del phi, not 2 del phi, or if it is 2 del phi, there should be some reason that right now I cannot tell you, later on I will see it. Anyway, so we will find out del phi. So, del phi by B, that from that graph we will get the basically that is the slope of the graph B versus del phi. So, that slope we can use for calculating the del nu for a particular wavelength. Now, we repeat for the second wavelength, third wavelength, fourth, fifth, we have 5 filter and corresponding Verdict constant you can calculate, and you plot it and you see how it depends nu, how it depends on the wavelength, whether it depends on the, if it depends linearly. So, we will get a set line, if depends some other form like A plus B by lambda square. So, it will not be straight line, there should be some curve, and that curve can be fitted with the some expression, and that expression generally comes like this. So, nu depends on lambda following this form. So, that one can find out from this experiment. Okay. So, now here as I told you, I will show you the, let me disturb it. So, now magnetic field, now you see I will take out this, how to change the filter I will show you. There is a, so I will take out this filter. Okay. This filter, it is a wavelength, one has to note down 505 nanometer, 505 nanometer. Okay. So, this wavelength one has to note down, and then you can use another filter, repeat the experiment I am not going to do. So, for 5 filter, 5 set of data you can get. Now, this is the polarizer and this is the analyzer. I have to disturb this one for, if I want to measure the this I will take out this one, this sample. Okay. I think one has to, yes, this you see. So, this is the pole piece, this is the gap between this, but its length is more than that. I cannot put this way. Okay, I cannot put this way. That means it is also inside this pole. Okay, some portion. So, I have to measure the magnetic field inside the pole also, that there is a hole, and through hole I am not going to disturb this one, because now then I have to remove all things. So, I will, what I will do, I will just, one has to disturb the setup for measuring this. So, just I have to, okay, and let me check whether I can put this one. I have to, okay, let me, I think I have to take more distance, but still I do not think. So, I can remove this, I can remove this, I can take out them, I can take out them. Okay. Okay. So, then actually I have to use this probe and put this EC, but one has to make it length more. Okay. Let me make the length more. This we have to make it proper alignment. Okay, slightly height I have to okay. Yes, slightly height I have to decrease. Yes, so I have to put along the axis. So one has to align it, you know. So then I think I have aligned. Yes, but it's not slightly more I have to go. Yes. So more or less it is along the axis. So you have to go, you see, I can go, I can show you the end. Okay. So this is the, you see, I am in at the middle position, okay, between the gap. But you have to start from the inside, you have to start from inside, okay. And then for this position, what is the, you see, if I apply current here, you will see the reading, okay. Here you can see the changing, I am applying current, okay. So how much current here I have put, say, let me put this 4, okay. Earlier whatever I have done, 1 for 1 current I am showing you, for 1 current I am showing you. More or less it is 4, okay. For that, you see, for this position it is, I have to note down 6.21 millitesla. Now I have to change the position, okay. At this position it is going out of the scale, so let me go there, okay. Still it is out of the scale because maximum current I have taken 204 millitesla, okay. So at the middle basically you will get maximum current, middle you will get maximum current, okay, 214. Now it will start to decrease 180, okay. I am going in, okay, this way. So for different position you have to measure the magnetic field using the axial probe. And other probe we use this way, you know, this way. Here also is same current, this way. If I put this way, you will not basically, you should not see any perfectly. If you see this way, there should not be any, but some reading is showing anyway. So it's it will not give the accurate magnetic field, okay, if I try to, and it is difficult to do that because condition of this one is one has to put this way, okay. So then you will get, so this also one could use because outside it we could use at defined position we could measure, but since sample is inside also, so that is why we cannot put this one inside of these pole pieces. So inside of the pole pieces we cannot measure the magnetic field using this one. So that is why we have to use this axial probe, okay. In axial probe condition, magnetic field will fall on this because this here I will explain you later in different class. So here whatever the sample for Hall probe, there we use a small size of a material, semiconductor material. So condition is here current, magnetic field, and we are measuring Hall voltage. These three has to be mutually perpendicular to each other, okay. So to fulfill this condition, here magnetic field has to fall on this, and to fulfill that condition, here the magnetic field has to fall in this direction, because there basically probe is, that material is put like this, okay. Here material is put like this, so magnetic field fall perpendicularly, and in that here magnetic field this material Hall sensor basically is put like this, okay. So that means field has to put like this. So that is the difference between axial probe and this transverse probe, and that is important to know for this experiment. Okay. So, this is the experiment. I should make it current 0 because I should not apply current more time, then this will be hot. I can see this become already hot. So, I showed you the setup, and then what are the individual component, how it works, that I explained, and what are the steps for the experiment and how to take the data that I explained you, showed you. Okay. So, basically one set of data I showed you, but for this experiment, as you know that for one data is not enough for getting the better result. So, a set of data one has to take, and then for that you have to plot graph. From that graph we find out the either the mean value or the we use the gradient. So, that basically gives the average effect, okay, thus reduce the error in the measurement. So, I think I will stop here. Thank you.